This slidecast will cover lists. We'll talk about single linked lists and double linked lists. Linked lists are useful for inserting and removing at arbitrary locations. The vector class was limited because it had insert and erase methods that took linear time in order for a loop to shift the elements when we inserted and deleted in the middle of the vector. So a linked list can add and remove elements at known locations in order one time. It's useful when you need to insert and remove elements frequently and at arbitrary locations. Now, when using a vector to maintain an alphabetized list of students at the beginning of the semester while students are adding and dropping the course, we have to shift all the names that follow the new person's name down one position before you could insert a new student's name. So if a student drops the course, the names of all the students after the one who's dropped would be shifted up one position to fill the gap. So if we delete Annabelle, we have to shift up all the remaining entries. To maintain a list of students who are waiting to register for a course, we could give each student a number, which is the student's position in line. And if someone drops out of line, then everyone with a higher number gets a new number that's one lower than before. And if someone cuts into line because he or she needs the course to graduate, everyone after this person gets a new number that's one higher. So the person maintaining this list is responsible for giving everyone his or her new number after a change. So this can be expensive and depends on the length of the line, how much work that might be. Here's a figure that illustrates what happens if Alice is inserted and given the number of 1. Alice is inserted after Emily. Everyone else has to get a higher number. Now, a better approach would be to give each person the name of the next person in line instead of her position in the line, which could change frequently. So to start the registration process, the person who's registering students calls the person who is at the head of the line, and after he or she finishes registration, the person at the head of the line calls the next person, and so on. Now, if person A lets person B cut into the line before him, ahead of him, because B has taken A's position in the line, then A will register after B, so person B must have A's name. And the person in front of the new person must all know to call B instead of A. So we're going to use this kind of idea to support a list data structure. Now here's a figure below that illustrates what happens when Alice is inserted in the list. So before we insert Alice, here's a person in line, and here's the person to call. So for instance, Emily knows that Fong is the next person in line, and Fong knows that Anna is the next in line, and so forth. So only the two entries shown in color need to be changed if Alice is inserted in the list. So if Alice is inserted in the list, then Emily now needs to know that Alice is next in the list, and then Alice needs to know that Fong is next. So this makes it so that Alice now becomes the new second member in the list, but only two other people have to make changes to the original data that was keeping track of the line. Now what happens if someone drops out of the line? In this case, the name of the person who follows the one that drops out must be given to the person who comes before the one who drops out. So here is a line. If Aaron drops out, then instead of Anna pointing to Aaron, Anna needs to be updated to point to Christopher. Okay, Christopher was after Aaron originally. So we only need to change that one entry, and then all the data keeping track of our line is up to date. So using a linked list, it's analogous to this process we just described for keeping track of the order of people in a line. And insertion and removal are done in constant time. There's no shifting required. Each element in a linked list is called a node, and it stores information about the node and a link to the next node in the list. So here's a description of a node, And here's a portion of a UML diagram. So a node is going to be a class or a structure, and it contains a data item. We'll say it's of item type because we'll be able to put any type of data into our nodes. Okay, so this is going to be a kind of a general, kind of an abstract definition. And then along with that data is one or more links. So a link is a pointer to a list node. So in our structure, a node contains a data field named data and a pointer to the next node named the next. So here's a picture of a list. It's a collection of nodes. Each of the nodes has a data value, Tom, Dick, Harry, Sam. And each node points to another node. Tom refers to Dick, Dick to Harry, Harry to Sam. Sam's next pointer is currently null, so he doesn't point to anywhere. Now here's a header file, and we're using a struct instead of class. And a struct is a data structure that contains data fields and possibly constructors. It's like a class, except it has no operators. So here it has data and next is a pointer to node. Here's a constructor. It takes a data item and a pointer to a node, and then initializes these two data fields using an initialization list. Now, a node is defined inside a class, making it an inner class. So the outer class is a template class that has the template parameter item type. The node is defined in the private part of the outer class, so it keeps the details private from the outer class's clients. And the reason for defining it as a struct is that a struct's data members are public by default, so they're accessible to the functions of the outer class. The constructor initializes the values of data and next, and we provide null as the default value for next.
This slide shows the C++ instructions to build a linked list that looks like the list that's pictured here. Now the first four statements construct new nodes with the given strings Tom, Dick, Harry, and Sam. And when we construct these nodes, their next values are initially the null pointer. So after these four statements, we have four nodes with a local a local variable Tom, Dick, Harry, and Sam. Now next, we create the links. And in this statement, a pointer to the node with the data item Dick is placed in the data field next of the node that's pointed to by Tom. Okay, so that's why here Tom's next value points to Dick, and so forth. Dick.next points to Harry, and Harry arrow next points to Sam. Notice we're using sort of the arrow notation here, not the dots, because Tom, Dick, and Harry are pointers. Now generally when we have a linked list, we don't have individual variables in our program that point to each node in the list. Instead, we'll usually have a pointer to the first node in the list, and we'll work from there. So we often call the first node the head of the list. So here we have this variable head, that's a node pointer, and we can assign that to be Tom. So Tom will be the head of the list. Here's a notation we can use to set up all the other pointers in the list without any additional variables other than head. So head arrow next refers to Dick. All right here, I guess this will create the Dick node with a next value of null. And then here, we'll create the node Harry, and we'll assign it to head arrow next, which takes us here, arrow next, which takes us here. And we'll assign that to point to Harry. And then finally, we can add Sam to the end of the list. And we can do that just by chaining together these reference to the next fields. So stop and study this code a little bit until you're comfortable with these references on the left-hand side. Now, on the previous slide, we grew the list by adding each new node to the end of the list so far. We could also create a list and add nodes at the front of it. So here we'd have a node head, which is a node pointer, and we generate the node Sam. And this second statement adds Harry to the list in front of Sam. So notice that each of these statements creates a new node whose data component is a name and whose next component is the list so far. So notice here, every time we construct a new node, we passed head as the second parameter, and head is going to be assigned to the field next in this node. So that's why the Harry node will refer to the list that includes Sam. Then when we get to the third one, the list with Dick at the front, or at the head of the list, will then point to the list with Harry and Sam in it. And then finally, Tom is created, and his next node points to the list with Dick, Harry, and Sam. Now, to insert a node in the list, this first statement creates the node Bob, and we have a local variable to point to that new node. And then if we want to insert Bob here in the list just before Sam, we'll say Bob arrow next gets set equal to Harry arrow next. So Harry currently points to Sam, and we're going to copy that pointer and assign it to Bob next. So step one here is that bob.next will refer to Sam. Our second step is to take Harry arrow next and set it equal to Bob. So in step two, now this node points to Bob. And now we've successfully inserted Bob into our list. To remove a node from a list, we need a pointer to the node to be deleted. So we'll have a local variable pointer that'll point to Tom arrow next. So Tom arrow next points to Dick. So PTR points to Dick. And then to remove the node from the list, we say Tom arrow next, which currently points to Dick in the gray, will get assigned to Tom arrow next arrow next. And Tom arrow next is here, and following next again refers to this data field. So this data field currently points to Harry. So we'll take this value and we'll copy it into Tom arrow next, which gives us this blue pointer. And that's all we need to do for a singly linked list. And then we delete pointer deletes the node Dick. So now we're just left with a list of 4 items. We use this delete statement so that the memory allocated to the node is removed so that we can avoid memory leaks. Traversing a linked list is a simple process. That traversing means to go through each element of the list in order. So we can set a node pointer to point to the first node, and then a while loop. While the node pointer is not null, we can do something with the node pointed to by node pointer, and then set node pointer equal to node pointer arrow next. Here, Tom points to the first node. So we'll say Tom, node pointer equals Tom. And while node pointer is not equal to no, in this case, what we're going to do with the list is we're going to output the data item, the string. And then we say if node pointer arrow next is not null, then we'll also output this sort of a double equals angle bracket, kind of an arrow symbol. Once we've done that, then we set node pointer equal to node pointer arrow next. We'll go to the next. That'll make node pointer point to the next node in the list. And then finally we have a cout when we process at every node of the list. So if we traverse the list with this code, we'll get a printout of all the items, and then sort of this is signifying a pointer to the next item in the list. This conditional right here makes it so that when we finally get to a node that has no, that's the end of the list, we're not going to print out a trailing arrow here. Now, single linked lists have some limitations. We can insert in the front in an order 1 operation, meaning no matter how long the list, it's a constant time to insert a new element or a new node in the front of the list. But inserting at other positions is on average order n. So insertion is convenient only after a reference node. If we already have a pointer to where we want to insert, then it's fast. Removing a node requires a reference to the previous node, and we can only traverse the list in the forward direction. So we can overcome these limitations by adding a reference in each node to the previous node. So this will create a double linked list. Here's a picture of a double linked list. We'll have a D node for a double node, and here notice it's the same as our node has been, except now we have another field called previous that's of type node pointer. Now here's a double linked list, and you'll notice the head of the list points, the first node in the list points to the next node. So we have this next pointer, and the last node in the list is set equal to null, but now each node points to the previous node in the list until we get to the first node and its previous data field is set equal to null. So here's a double linked list that will allow us to traverse in both directions. Here's the dnode class. It's also a struct, just as node was. We're going to use it as, we can use it as a nested class in a list class, and we've added this previous data field, and then here's our constructor. Our constructor takes a data item, and it takes a previous value and next value, which are the forward pointer and the backward pointer in our list. And notice these are optional parameters. This equals null means that if someone calls the constructor and doesn't provide these parameters, then they will be assigned null by default. And then here's an initialization list where we assign, we initialize the 3 fields in our structure. Now inserting into a double linked list, here we have a portion of a double linked list. We've got this node Harry and this node Sam, and we also have a local variable that points to Sam. Now if we want to insert, I think, between these two nodes, here's the C+ code. Here's the C++ code to do this, and we have our picture to help us conceptualize what's happening. First, we create a node, Sharon. So here's this new node. We have a local variable that points to it. Next and previous are null, so they don't have any values. Now Sharon arrow next, we set it equal to Sam. So Sam is this local variable, and it points to the Sam node, and we're going to make a copy of that pointer and assign it to next. So now the new node Sharon has a pointer to Sam. Then Sharon arrow previous, which is this value, it's set equal to Sam arrow previous. So Sam previous is this data field here. It currently points to Harry, so this pointer will be copied and be assigned to Sharon previous. So now Sharon points to Sam and Harry. She's kind of logically inserted in between those two fields. Now we need to update Harry and Sam to not point to each other, but instead point to Sharon. So Sam arrow previous arrow next, we say Sam arrow previous points to Harry, and arrow next is this data field here. Instead of pointing to Harry, this assignment will change Harry's next field to point to Sharon. And finally, we have Sam arrow previous is going to be assigned Sharon. So that updates this data field. And now we've correctly inserted Sharon into our double linked list. To remove a node from a double linked list, we have a variable Harry that refers to this node that we want to remove. We'll say Harry arrow next, which points to Sharon. Harry arrow next is this pointer to Sharon, and we'll assign that to Harry arrow previous arrow next. So Harry arrow previous takes us to this node. Arrow next is this data field here. And we're going to assign that Harry next. So Harry next points to Sharon. So we're copying this pointer here, and we're going to replace this field here so that Dick now refers to Sharon as the next item in the list. And then we take Harry arrow previous. So Harry previous is the pointer back to Dick, and we assign that to Harry arrow next, which refers here to Sharon, and then arrow previous is this field here. So this field is currently pointing back to Harry. We're going to change that so it now points back to Dick. Now we can call delete on the Harry node. It will disappear, but the pointers for the Dick and Sharon nodes now refer to each other. So that's how we'd remove Harry from a double linked list. Here's another picture of what it looks like. So Harry's now gone from the list. So the original gray pointers that pointed at Harry have been updated. So now Dick in step 1 refers to Sharon, and Sharon refers back to Dick. So far we've worked only with internal D nodes for a linked list. So a double linked list object has data fields. It has a head to point to the first node in the list, and a tail to point to the last node in the list, and num items is the number of internal D nodes in the list. So this is an object that keeps track of our list. And then notice our list contains node objects, and it can be of any arbitrary size. Now circular double linked lists have a link the last node to the first node and link the first node to the last node. So the first node in the list, head arrow previous, its previous value refers to the tail of the list, and the tail's next value is equal to head. Okay, before we had a circular list, remember these values are null in a single linked list, but in a single or a double linked list. But a circular double linked list will have these two additions. So we can also build a single linked circular list where the tail points to the head, and then that would allow us to traverse in the forward direction only. And if we keep a pointer to the tail, we can access the last element and the first element in order one time. So the advantage of a circular list is that you can continue to traverse even after passing the first or the last node. So we can continue to access the list in a circle. We can visit all the elements from any starting point. We can start anywhere in the list, and when we get to the end of the list, we'll cycle back around and continue on to where we started in either the forward or the backward direction. So you never fall off the end of the list. And the disadvantage is that our code has to be careful and avoid an infinite loop. Here's an example of a circular list. Here are all the nodes. There's 4 internal nodes to the list. This first object here is a list object. For circular list, it points to the head of the list, the tail of the list, and keeps track of that we have 4 items. And notice this looks like a double linked list, except that the previous value at the head of the list now refers to the tail, and the next value at the tail of the list points to the head. That brings us to the end of this slidecast.